Okay.
I
Yeah, it's okay. I understand it's my mistake, but you should tell me immediately when the class starts. Okay. So I started it now. So let us go through it a little bit faster again. So the idea is to simplify the system. Uh, so if you have some matrix A, we have learned that we can write that if you have all the eigenvectors of A are real eigenvalue, then you can write it P J P inverse in the form of A. And the idea is that this helps us decouple the linear system with constant coefficient. How? For example, if A is diagonalizable, then you can do this simple manipulation and basically you get this thing. Okay, and similarly so in the end you get a very nice this matrix. So this works only if A is diagonalizable, and this matrix is basically the matrix for the fundamental solution. Similarly, if A is not diagonalizable, but then you can write the Jordan block form, Jordan canonical form. Okay, and this is the Jordan canonical form where J, if it has only one eigenvalue, looks like this. Okay, and in that case, for example, for 2 cross 2 blocks, the solution looks like this. For 3 cross 3 blocks, the solution looks like this. In general, we can write down a solution for a arbitrary size of block K. Okay, so j if j is basically k cross k, so it will be lambda 1 and so forth, something like this. Then I'll just simply write that z of this is a lambda t 1 t square by 2 goes till t k minus 1 factorial. Okay, and now you just keep shifting by one index. Okay, and in the end you will get 1 here. Okay, and this you multiply with, so ck, so this will be k cross k. So this is the solution you will get corresponding to that. Now of course you can have mixed situation where you have some corresponding to some eigenvalue you will have all the eigenvector. For some you might not have all the eigenvector. It doesn't matter. In the case you can always get a matrix, you can just divide them into blocks. So in general your matrix A can be written like this, right? So let's not write D, let's write it J only. Okay, and then J will either will be consist of these blocks. Okay, and these can be either diagonal, and each block is either diagonal matrix or a Jordan block. Okay, so this is Jordan canonical form for arbitrary matrix. And then you can repeat the same process. In the end you will have you have this matrix P, and if you do that matrix P, the terms corresponding to diagonal case will go to the case something like this. Terms corresponding to the Jordan blocks here will be something like this, depending on the size of that Jordan block. So in the end you can decouple the system, it doesn't matter what is the situation. And this allows you to basically solve the linear systems with constant coefficient. Okay, now the only thing left is the case when you have convex eigenvalues, and let us look at that case also. So okay, before so in convex case, let us recall. So if you have convex roots, sorry, complex root, I'm saying convex, complex roots, and your roots will be something like alpha plus minus I beta. Okay, then if you can recall, your general solution was something like this. So here I'm going other way around. Here is, because you already know the solution. And then there was another thing, something like A minus IB E alpha I beta T. So this is, of course, this has complex components in the vectors also. So in this case, if you can recall, you took only the real part and imaginary part and you declared them to the solution, and that is indeed the case. In this case, you consider the matrix P of vector A and vector B. Okay. And you write J, the corresponding Jordan blocks, to be alpha plus IE beta and alpha I minus beta. Okay. And then the solution matrix will be basically P E alpha plus I beta T, 0 E alpha minus I beta T, 0, and of course P inverse. And this is the same case for the diagonal case. If you recall that in the case of your diagonal situation, because you have distinct eigenvalues, so you get distinct eigenvectors. Either you consider them or them, but in the end you have to write the real solution, and this is the way to write the real solution. Okay, so this is the fundamental matrix. Of course, then you can multiply with this constant, and of course they will be in a pair of 2 and 2. Otherwise, then you find the other one, missing one. All right. So now, once we have done that, let us combine this discussion in a way which makes it very similar to the discussion what we had for the first order ODE case, or the first order ODE case, where x was a scalar, not a vector. So in that case, if you can recall Picard's iteration, okay. So I'll write down the Picard iteration for the system and for the linear system to be precise. This for our case will be equal to I, sorry, not I. Okay, before that I want to define something, then I'll come back to it. Okay, now let us define two things. One you already know, this is called fundamental matrix. And the fundamental matrix was nothing but the matrix of the n linearly independent solution. Okay, so the fundamental matrix of a system x prime ax is matrix valued function. It is basically a matrix whose columns are linear independent solution of the system. Not that this also means that the fundamental matrix is always invertible because the columns are linearly independent. Okay, this you already know. What I want to specify is a particular fundamental matrix, which makes it more interesting, and it will be clear in a second why it's interesting. So a fundamental matrix is called principal fundamental matrix. Principal fundamental matrix. If the solution, the n linearly independent solutions of the solutions, column solution, let's say, okay, which make this matrix satisfy. So if X is this fundamental matrix, let's call it X only. Then at 0, this is identity. Okay, so what where I is identity matrix. So what precisely I mean by this is that once you find one X, let's say you found one fundamental matrix, any fundamental matrix. Okay, let's call that fundamental matrix to be capital Y. Of course, if you evaluate this, the solutions of the systems will be then X is equal to this matrix Y multiply with some constant vector C. Agree? This is general form of the solution. Agree? Do all of you agree? Y can be any fundamental matrix. Yes?
Yes, sir.
Okay. Now, what we want to convert from Y, we can get this principal fundamental matrix X such that it satisfies a particular set of initial conditions. How? We will solve it in such a way that now my initial conditions, note that these C's are uniquely determined by the given initial condition. I want X0. So let's say I want my first linearly independent solution to be satisfying the initial condition, something like this. Similarly, I want my second linear independent solution to satisfy initial condition, something like this. And I want my nth vector solution, so this will be nth solution, to be satisfying this initial condition. Okay, so for each initial condition you'll get one C. Okay, so basically what I'm going to do is that I'm going to put one initial condition, I get one C, I got find another fundamental solution, I get another C, and so on and so forth. And by once I solve these n initial, so I have to solve n initial value problem. Okay, solving this n initial value problem, I get this solution. Okay, and then that will be my principal fundamental matrix. Note that once it's enough if you find one this fundamental matrix, because after that you have to just solve this n linear system, which is basically equivalent of finding Y inverse, right? It's effectively finding Y inverse. So the C will be, so this yeah. So you see that once you know Y inverse, each time it's become trivial to find this C. You just multiply this with this side of the vector. Okay, this side of the vector is identity, so you get this C uniquely. So basically the fundamental matrix X, if you see carefully, will be basically Y matrix C, where matrix C is nothing but what it will be? Okay, you work it out. What will be X from this discussion? You see that if you know what is Y inverse, then the you already know what will be the X1. X1 will be sorry, C1 will be Y inverse of this. So what you will get is that yeah, you will get Y inverse of these matrix. Yeah, okay. It's not important, but you can do that. Okay. All right. Now from this discussion, the direction I want to take is a little bit different. So that's why I stopped here. What we want to know is that how to find this fundamental matrix in much easier way instead of looking at this. Okay. Because there it involves inverting this thing. All right. So now let us look at this Picard iteration. Basically, Picard iteration is used to solve the system here. So everything is a vector here. And because I want my initial condition to be identity matrix, I put I here and 0 to T A S phi of S ds. Okay, so note that everything is a matrix here, not a vector. Everything is a matrix. So this is also a matrix. This is a matrix. This is a matrix corresponding to the initial condition, solution of the initial condition. These. Okay. Now, when you do the Picard iteration for the system, they are called Peano-Baker series. And how the Peano-Baker series looks like. So the first one, of course, will be identity matrix. The second one will be equal to identity plus integral 0 to t a s phi 0 s ds. Okay. Here this series is true even when A is not a constant matrix, even with the depending on this. If it is constant matrix, it simplifies. And similarly, you can define phi 2. This will be I plus 0 to t 0 to s, and you can just write A tau phi 1 tau d tau ds. Okay, so you keep doing the, okay, so before that there will be one more term here. Okay, this will be integral 0 to t as ds. Okay, so this is exactly like Picard iteration but for the system. And then when a is constant, it's much simpler. So what you can get is that in this case phi of t, I'll directly write down the series, is going to be I plus integral 0 to t a of ds, as you can see, plus 0 to t 0 to s a square dt ds, and you can keep doing these integrals every time. In every next term you have one additional integral. Now because a is constant, you can take a out, so you get a of t plus a of t square by 2, and similarly you get a tn by n factorial plus something like this. Now this matrix, this is a matrix, not that this is a matrix, is called exponential matrix of this one. So you know that this is a matrix, and this matrix we define to be exponential of a matrix AT. T is a scalar, A is a matrix, so this is a matrix, and I'm defining it exponential function of a matrix like this. And how do you find such an exponential matrix? So given a matrix A, our aim is to now find a exponential matrix. Okay. That exponential matrix of AT, when t is equal to 1, of course, it will be exponential A. Now, it's very easy to do if you know the ODE. And how to do that? Let us note that the series I plus AT plus A square t square by, sorry, this is square, this is n, 2 factorial plus so on and so forth. This, if A is either diagonalizable or Jordan form, either way, if it's diagonalizable, then it will be I plus P dP inverse T plus P d square P inverse T square by 2 factorial and so on and so forth, assuming A is P dP inverse. Okay, and that I can write in a neat form is equal to P, I can take out common, I plus dt d square dn by n factorial, sorry, yeah, dn by n factorial and tn, okay, and so on and so forth. This is P inverse, this is P. Now dn is nothing but lambda 1 power n, lambda 2 power n, and so on and so forth. So this I can write it in a nice form, something like exponential of e lambda 1 t 0 0 0 0 e lambda 2 t e lambda n t P inverse. Only thing is that I have to assume that this series converges, and it converges actually, right? This converges to this. You can check in the any vector now, it will converge. Okay. So with this, what you get? This is equal to P E dt P inverse. And if you see what is this? This is exactly, let us go back a little bit more back, this. And this matrix P is same matrix P. So if you know the solution of the corresponding ODE system, you can find exponential of the matrix. Okay. So how would you do? If A is diagonalizable, you write the diagonal entry like this, find this matrix P which are consist of eigenvectors, and do that. And this is the case when A is diagonalizable. When A is not diagonalizable, that means when A is A can be written in the Jordan form, then you repeat the same process. Okay. How would you do the same process? This will be, so if A is equal to PJP inverse, then exponential of AT, okay, will be P E JT P inverse. Now here this thing is exactly this thing. This thing for each block. Okay, for each block, this is how it looks like. Of course, if some of the blocks, it might not be the case. All right, so with this, we can find for any matrix A whose eigenvalues are real, it's exponential matrix. When eigenvalues are complex for certain part, when it's a complex, I already told you what will be the fundamental solutions. Okay, so let's go back and let me explain this one. So here, if it happens to be complex, then this will be that exponential part, and not that even when you have some complex values here, this is real. Okay, in the end what you'll get is real, because you will compare the real and imaginary part, and this is what you'll get. Okay, so with this you can find exponential of any matrix. Okay, more precisely, from this we should also conclude certain things, and I want to conclude in particular two remarks, and then we'll stop after that, and I'll take your question. First remark, if phi1 and phi2 two fundamental matrices of x prime ax, then phi1 is phi2 multiply with some constant matrix for some constant matrix A. So constant matrix C. Okay. If you now let's go back to the discussion what we are having here, how to find this given any fundamental matrix Y, how to find the principal fundamental matrix, and that is pretty easy as I was trying to explain there, and then I left it. Assume that phi is a fundamental matrix. Let us write in the next one, remark 2. If phi is the fundamental matrix, okay, then let us define a new matrix phi of t. This is phi t, phi 0 inverse. This will be fundamental matrix. Of course, it's a fundamental matrix because for any C, this will be for any C, this will be fundamental matrix. So this is some constant C, so this is a fundamental matrix. But what I want to say is the principal fundamental matrix. And why this will be principal fundamental matrix? Because you know that at 0, this will be phi 0 multiply with phi 0. So this is identity, and this is how you identify the principal fundamental matrix, that at 0 it becomes identity matrix. Okay, so now note that this phi t, so this principal component matrix is nothing but E of AT. So if you find this is the way to find, you see that what is this? This thing is nothing but this thing, which is also this thing. Why? Because note that at t equal to 0, this matrix is identity matrix. Okay, and this is the fundamental property which helps you identifying the principal fundamental matrix, that at 0 it should be identity matrix. Okay, so how to find exponential of AT? You find the fundamental matrix. Okay, and the fundamental matrix, basically this we know how to find, right? Either you find any fundamental matrix and then multiply its inverse, multiply that matrix with its inverse on the right hand side, then you get the thing. And note that this also comes from the discussion what I'm trying to have there, but a little bit faster. Where I was having this discussion here I was having these discussions. So this C will be nothing but the y inverse of component of y inverse at 0. So then this becomes a fundamental matrix. This sorry, principal fundamental matrix. Okay, so with this we stop the discussion for the systems, and I will take your questions now. The aim here was that to tell you that you can define exponential of the matrix, something like this, by solving system of ODEs like this. So you solve a system of ODE, find its inverse at 0, multiply this, then this will become exponential of this. Okay, and this you can do it for any matrix, not only for the real eigenvalue, you can also do it even when you have complex eigenvalue. So try to try to find. I will upload some notes for this part and some part which I covered before, but I haven't gone into details because that's a part of your first year thing. Okay, so today itself I will upload all the notes for this discussion and discussions about systems and hierarchy which was covered in your first year syllabus. Okay, so with this I stop the recording and then you can ask me questions.